Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about posterior predictive distributions. Our discussion will be centered around data with a binomial likelihood and a beta prior for the parameter pi, the probability of success in any given trial. So, let's begin. First, what we are going to be doing is going over the main ingredients to analyze data from a binomial likelihood in a Bayesian manner. And then we will describe the problem that we want to solve. Make sense? Okay. So, as you know, right, from what we have been doing thus far, to carry out statistical inference from a Bayesian perspective, we need two main ingredients: the prior distribution and the likelihood function. Okay, so first let me just remind you that our parameter of interest is pi. It's a proportion. Pi. Then, as we said, we need a prior, and since we consider our parameter of interest pi a random variable, that prior is a probability distribution that reflects our beliefs about this parameter. Then we have the likelihood function, right, which could be thought of as a conditional probability, the probability of observing our data given a particular value of the parameter pi. And in this case, we are going to have data that could be modeled using a binomial. Okay? Now, our posterior distribution would be the following conditional probability, right, or probability distribution. The probability of pi given the observed data, given our sample. And the problem that we want to solve here is this. We want to compute or find the probability of getting y star successes in a future sample of size n star. And let me use notation to kind of summarize the problem that we are trying to solve. We want the following conditional probability: the probability of observing y star successes given that we have already observed another sample, right, y. Okay, so now let me define what we mean by predictive posterior distribution. So definition of predictive posterior distribution. So it will be the probability of y star given y, and in this particular setting it will be given by the following integral, the integral from 0 to 1 of the probability of y star given pi times the posterior distribution of pi. That is the probability of pi given y. And we are integrating with respect to pi. Make sense? So can you see that by doing this we are incorporating our initial beliefs and the information coming from our sample, our initial sample y, right? The posterior distribution takes into account both sources of information, and then, right, we want to compute the probability of y star given a particular value of pi, but we take into account, you know, that information coming from our data and our initial beliefs with the we capture that with the posterior, right? So we do this for every single value of pi from 0 to 1, right? Can you see it? Okay, so now comment. Let's talk about you know, a situation which might be simple, and it's going to give us you know, a better understanding of the predictive distribution. So when n star equals 1, right? And by the way, before I move on, let me just point out something, right? Remember that y star is the number of successes in a future sample of size n star. So what that means is that y star could assume the following values, right? 0, 1, 2, 3, up to n star, right? Okay, so now back to that comment I wanted to make, right? Hopefully this is going to help us have a better understanding of what we mean by a predictive posterior distribution. So if we had a future sample of size 1, what we mean is a single future observation, a single one, okay? So we could compute that probability for y star equal to 0 or y star equal to 1, right? So seeing 0 successes in a sample of size 1 or 1 success in that sample of size 1. Now let's use the definition that we have here. Make sense? So now, what's the probability of y star being 0 given pi? Pi represents, remember, the probability of success. So the probability of seeing this would be what? 1 minus pi, right? So it would be 1 minus pi minus pi. Okay. Now, using the linearity of integrals, we could break down that integral into 2. So it would be the same as just 1 times this, right? Then plus, and then we would have that integral from 0 to 1 of pi. We should have a minus here, right? Times the posterior, and we integrate with respect to pi. Now, the posterior distribution, right, is a legit probability distribution. So the integral from 0 to 1 in this case of this guy is just going to be 1, right? And this guy here, if you take a look at it, it's expected value of pi given y. So that guy is the conditional expectation of pi given y. Or in other words, that is just the posterior mean. Make sense? Now, for y equals 1, when we use the definition, we just go, oh, the probability of seeing one success, if the probability of success is pi, will be just pi, right? So would be this guy here. Oh, let me copy that integral. Oh, come on. Well. Just let me copy paste this one. This one will be just pi. Oh, come on. There we are. Right? And that happens to be just the conditional expectation of pi given y. So as you can see, this, right? These guys are a legit probability distribution. The sum of these guys is 1, and the expected value is going to be positive, and 1 minus expected value, well, it's going to be positive as well, because pi lives between 0 and 1, so the expected value must be between 0 and 1, right? Okay, so can you see what we mean by that? And something interesting here as well. Our prediction, our predictive probability, right, for seeing one success in a future sample is given by the posterior mean, right? So posterior mean. Okay, so now let me give you an example, right? Let's go back to an example that we talked about. I think it was in week 3. Okay, remember that problem? It had to do with the proportion of students who would quit the University of Iowa if tuition were raised by 19%, right? Okay, so in that case, what we had, let me remind you about that problem. What we had example, what we had was this. We had a prior probability distribution that reflects our knowledge or ignorance about pi. In that case, what we said is, let's use a beta distribution with parameters alpha equal to 10 and beta equal to 40. Now let's use in that case, right, we know that this guy, the kernel, that means the expression of the PDF ignoring the constant that makes it so the area underneath the probability density curve is equal to 1, right? So ignoring that constant, we know that the kernel, right, looks something like this. Pi to the power 10 minus 1 times 1 minus pi to the power 40 minus 1, right? So that's a prior. Now, likelihood. So in that case, right, we had information about a sample of size 50, and we observed 7 successes. Y was equal to 7. Okay. Now we're going to be doing something similar with the likelihood. We know that that guy will be the probability of y given pi, and it would be proportional to, right, pi, the number of successes, would be 7, so pi to the power 7. Then we would have 1 minus pi to the number of failures, so that would be 43. Okay, and we also know that the posterior in words, right, we know that the posterior is proportional to prior times our likelihood, and in symbols, then the probability of pi given y, right, this one is going to be inverted. So this guy is going to be proportional to this product here. Then what we're going to end up with is 17 minus 1 and 83 minus 1. So just from looking at that kernel, we go, oh, right. So it seems that the posterior distribution has a beta distribution with parameters, and we use the following notation. Alpha star represents the parameter for our posterior, right? So it would be alpha is going to be 17, and beta star, the new beta, the one for the posterior distribution, would be well, 83, right, this guy here. So if we wanted to predict if we wanted to predict the probability of another student, not one of those 50 included in our initial sample, if we wanted to predict the probability of that student quitting school due to an increase in tuition, right, of 19%, then that would be the kind of problem that we wanted to solve, right? What's the probability that y star equals 1, given that we already have observed y, right, which represents the information coming from that sample, right, of size 50. So what we know now is that this guy happens to be the same as the posterior mean, right? And we know that for a beta distribution, right, the mean is given by the following formula. In this case, alpha star divided by alpha star plus beta star. So our prediction for that probability would be 17 divided by 17 plus 83, that's 100. So that's 17%. Make sense? And then if we found the probability of y star being 0, we know it's going to be given by the complement, right? So 1 minus this, and that's what we showed here, right? So in that case it would be 1 minus 0.17, which of course is going to be 0.83. And clearly these two guys form a legit probability distribution. So this is what we refer to as the predictive, as the posterior predictive distribution, right? Posterior predictive distribution. Okay, so let's summarize what we did here. Okay, so in this video we wanted to answer the following question. Hey, I want to find the probability of getting y star successes in a future sample of size n star. How do I go about that? The answer is use the predictive posterior distribution. So the probability of observing y star given information coming from an independent and previously observed sample y, right? So, and the definition is, in this case, for this kind of likelihood, the integral from 0 to 1 of the following product, the probability of y star given pi times the posterior, and then we integrate with respect to pi. Okay, so and then we used that definition in general for the general case when we are interested in just a sample of size, a future sample of size 1, right? And what we realized was that the probability of y star being equal to 1 given y will be the same as the posterior mean, and the probability that y star equals 0 is going to be the complement, 1 minus the expected value of pi given y. Again, this is the posterior mean. And finally, just we talked about an example so we can see things more clearly, right? In a more concrete way. So clearly these two guys form a legit probability distribution. Make sense? Okay, so that's it for now. In the future, in another video, we are going to talk about another example where we have a future sample size greater than 1. Okay? But that's another video. Anyway, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.